Chapter 6 is about discrete probability distributions. Discrete not being a new word to us at all. We just know that that's countable. There's not an infinite amount of variables that are going on here. So in section 6.1, we're going to learn about discrete random variables. So like I said, this first page, guys, is really nothing new. Let's talk about it, though. Objective 1, let's just make sure we remember the difference between discrete and continuous random variables. Before we talk about those specifically, we just remind ourselves what a random variable is. It's a numerical measure of the outcome of a probability experiment, so its value is determined by chance. Random variables are going to be denoted using letters such as X. So remember, this makes it sound way cooler than like a random phenomenon. No, anything can be a random or a probability experiment if we don't know the outcome, right? So you guys taking this test or this class is even a probability experiment where the outcome is kind of determined by chance, obviously a little bit more depending on whether you're studying or not. They use P of X a lot in this section. And so you'll probably see that quite often. So what are some values of random variables? The heights of students. Values on a die. I just put etc. We can really make anything a random variable that we're studying. Basically, all the stuff we talked about in chapter 1 can be a random variable. So help me fill in the blank. Which random variable has a finite or countable number of values? Discrete, you got it. So in test 1, you had to determine whether it was discrete or continuous. Remember, discrete was countable, 1, 2, 3, 4. So again, I could start naming tons of stuff. I have the number of A's, in course, number of contacts on phone, etc. The number of A's and the number of contacts you have are just nice whole numbers that you can count. There's not 1.5. There's not this continuous amount. So which one does it leave where you have an infinite amount of values? Continuous, right? And we'll talk about continuous probability distributions in chapter 7 and chapter 8, all right? So continuous is the speed of a car, ounces of water drank, etc. Bless you. Speed of a car, because it has to be measured with a speedometer. Ounces of water, because you're measuring it with ounces and so forth. So remember, if you're measuring it, it's continuous. So your first chunk of 6-1 homework is really repeat from chapter 1. It'll give you a variable, and it'll ask you to choose whether it's discrete or continuous, okay? So countable, it's going to be discrete. If you have to measure it in any way, shape, or form, it will be continuous. So nothing new there so far. Objective 2, even though it's technically new, it's new in the way that they're calling it, but it's something that we've seen since chapter 5. The probability distribution of a discrete random variable x provides all the possible values of that random variable along with their corresponding probabilities. So it's just like those distributions we saw in chapter 5. A probability distribution can be in the form of a table, graph, or mathematical formula. If you remember, I showed you an example in our book where it was the M&M colors, right? Blue, red, green, yellow, brown, I don't remember. But then it had their percent of what color was red, blue, and so forth. That was a probability distribution because it had the outcomes and the corresponding probabilities. So, what were the two underlying rules of chapter 5? Those same rules apply in chapter 6. Do you remember what this big sigma means? Addition. The sum of all. What do all the probabilities need to add up to exactly? 1. So that same rule applies in chapter 6. So when we talk about probability distributions in chapter 6, we want to make sure all the probabilities add up to 1. What do all the probabilities have to be between what two numbers? 0 and positive 1. You got it. Remember, a 0% chance was an impossible event. I don't know if anybody put that down for their extra credit. So that was an impossible event. And 1 is called a certainty. It was for sure going to happen. So here's a really boring example, but maybe this is the number of kids people have in the class, okay? So 20% of people have 1 kid, 60% of people have 2 kids, 1% of people have 5 kids, and 1% have 6 kids. Is this a probability distribution, yes or no? Rule number 2 is really easy to check. Do you guys agree that all of those values are between 0 and 1 individually? Yep. And then what do you get when you add them all up? 1, because this is 0.8, 0.9, 0.1, 1.0, okay? So this is a probability distribution. So your second chunk of homework is pretty easy. Once you get past distinguishing between discrete and continuous variables, they're just going to throw some potential probability distributions at you, and you have to say yes or no, okay? The test will be like that as well. I'll say yes, why, or no, why not. All right, are there any questions on page 1? Nothing new so far. All right, the top of page 2 is kind of new. It wants to show you a visual of probability distributions. So it says in the graph of a discrete probability distribution, the horizontal axis is going to represent your values. So in this case, you'll notice our values for 0, 1, 2, and 3. And then the vertical axis will represent the corresponding probability. So notice all the probabilities are up here on the left in decimal form. And then, of course, depending on what your outcome is, it goes to that height, all right? So suppose we ask a basketball player to shoot 3 free throws. Let the random variable x represent the number of shots made, okay? So if this person's shooting 3 free throws in a row, what's the probability that they make none? Where is that sitting at? 0, okay? What's the probability that they'll make 1 of the 3 free throws? 0.1 or 10%. What's the probability that they'll make exactly 2 of the free throws? You kind of have to eyeball that one, like 0.38, 0.37, something like that, not quite 40%. And then what's the probability that they make all 3? A little bit more than 50, maybe 52%, okay? And that's all it's doing is showing you the outcomes and the probability that that happens. What should we get when we add all 4 of these values up? 1. Notice none drop below the x-axis or anything like that. So I know you guys don't care and you don't really find it that interesting, but every 3 years we have to relook at new books, okay? And even if our same book by the same author, we have to upgrade to it. And it's kind of annoying because to me it causes the students a lot of money. And there's hardly any changes, but one of the changes most recently was this. They used to draw it with a histogram. Do you remember what a histogram looks like? It's a bar graph. And the author changed it to this, and I read why, because I'm like, well, that's interesting. What was wrong with the histogram? Why did they go from a histogram to these skinny little lines? And I read, and the reasoning makes sense. They said a histogram, they share sides, right? So it's almost like it's a continuous variable where there's no gaps, right? You go from 0 to 1 with no gaps. But a discrete probability, you either make 0, 1, 2, or 3. There's no in between. And so they wanted to really show that it's discrete. It's countable. It's not like, you know, this way or that way. It's obviously 1, 2, or 3. So that's kind of interesting. So really, guys, this is equivalent to the relative histograms that we've dealt with, but instead of drawing a bar, you draw a vertical line, and that's the only difference. Okay? So objective 4 is really the only new stuff so far, okay? So once we get these discrete probability distributions, for example, this free throw shooter, we want to start knowing, okay, on average, how many free throws should this basketball player make? And so we can start finding the mean, all right? Let's look at this formula and see if we can dissect all those crazy things. What does mu always stand for? The mean, right? That's your population mean. That's your population mean. What does it have? It has a little baby, it doesn't look that little, but that's a subscript x. It just means it's the mean for the x variable, okay? I typically don't use x, but you'll see it on your calculator and so forth. What does big sigma mean? Sum. And what are we going to sum? We're going to sum the stuff that's directly to the right in the brackets, okay? The x is the variable. And what's P of x stand for? The probability. So what it wants us to do is to take that random variable and multiply by its corresponding probability and do that again and again with every pair and then add it all up, and you'll get the average, okay? Since x is the random variable, p of x is the probability. So let's do it with this example right here. We'll do this once by hand, but guess what your calculator does for you? This. This isn't horrible to do by hand, but we're getting to standard deviation. It's a little bit more consuming. So it says compute the mean. So it's asking for mu. It wants us to find mu, right? Of the discrete variable given in the following table. Let the random variable x represent the number of classes a student takes, okay? So this is the probability that someone takes one class in a semester is 16%. The probability that they take 2 classes is 22%. The probability they take 3 classes in a semester is 28%. The probability they take 4 is 20%, and the probability they take 5 is 14. And hopefully that makes sense. A lot of you guys, if I went around the room, are probably closer to that 4 or 5 classes. But I feel like you guys aren't like the normal students. Like if I just went around campus and asked randomly, how many classes are you taking? How many classes are you taking? On average, what would our answer be? Okay, so we're going to find mu. So mu is take your outcome 1 times its corresponding probability of 16 plus take your outcome 2 times its corresponding probability of 0.22. Take your outcome 3 times its corresponding probability of 0.28, and you see what we're doing, right? This is also called a weighted average, like your GPA is calculated this way. Your course grade in here is a weighted average, right? Your tests are weighted a little bit more than your homework and your quizzes. So all you're going to do whenever you have to find the mean, if you want to do it by hand, I probably wouldn't do any of this by hand, is you just take your probabilities times your corresponding outcomes and add them all up. Remember, what we are getting is an average, so it does have a unit. What do you get to 2 decimal places? What do you guys get? 2.94, does that sound right? And I asked you 2.94 what? Well, what was our random variable x representing? It was representing the number of classes. So it's 2.94 classes. You got it. And I always like these questions, what does that mean? Because I know that's what's going through your head. You're like, okay, I got 2.94. I did the calculation. What the heck did I just find? Well, remember, an average is what you expect to find. So if I go around campus and ask people, how many are you taking, how many are you taking, I just add it. On average, we will approach 2.94 classes. So let me write that in words. The more people you ask, the closer the average will approach 2.94 classes. The more people you ask, the closer the average will approach 2.94 classes. Okay? What I'm going to do, I'm going to go around the room real quick and ask you how many classes you're taking this semester. I want to see what our average is in here, and I would guess that it's higher than 2.94. I would guess that it's closer probably to 4. Taylor, how many are you taking?
5.
5?
5.
5?
4.
4?
3.
3?
5.
5?
4.
4?
4.
4?
4.
4?
5.
5? 3? Gosh, guys. 2. Yeah, and you feel like a slacker, right? When 2 classes is a decent load. Yes, sir. Seth. 4? 5? 4? 4? 4? 4?
The classes I used to have?
No, just this semester. How many are you taking this semester?
But I dropped 1 class, that's why.
Oh, okay. No, how many you enrolled in the beginning? That's fine.
Used to take 4?
4, that works. I'll do it. And how many people are here today? 4, 8, 10, 16, 19. 4.05. So that's exactly what I said, okay? But I said, like, you guys are not the normal crowd. Usually that people take this class are going towards a higher level of education and so forth, where at Lewis and Clark, a lot of people are just coming for one class or two classes. So instead of just asking you guys, I go around and start asking more people what's going to happen to that average. It's going to drop. Will it be exactly 2.94 right off the bat? No, maybe I'll drop to like 3.8, but then I go ask more people what's going to happen, drop to 3.2 and so forth. So the whole idea is this average can't actually happen, right? 2.94 classes, you can't take that, but averages don't have to be perfect, nice little whole numbers. You know that in this class, no, sorry, the class I teach in the beginning, there's an older gentleman that comes in right after my class that I teach, and I'm talking to him, and he's talking about what math classes he has to take. I'm like, well, what degree are you going for? He goes, oh, I already have 2 doctorates. I'm not going for a degree. And my jaw just drops. I'm like, well, why are you here? And he goes, well, whenever I got my doctorates, math was not like a huge requirement, and I want to take physics. So he's this older gentleman that's retired that just wants to go back to take physics, but you need Calc 1 to take physics. So he's starting in intermediate algebra and working his way up to Calc 1 so he can just take physics class for fun. Doesn't that blow your mind? Like, it's crazy. Like, he has 2 doctorates already, retired, has a salary coming into him, and I'm like, wow, come on, can I steal you? Can you be in my class? And he's like, sure. Anyway, so that's off subject, but he would bring our average down, right? He would be that one of few people that only take one. All right, let's do this on our calculator. So how many of you guys are going to retire and come back to take Calc 1 so you can take physics later? I won't even do that, and I like math.
That's a waste of money.
So on our calculator, we can compute the mean using our list. All right, guys, so I believe this is the exact same data that we're using in our calculator. So what we're going to do is our step 1 is to put your outcomes X in list 1. And step 2 is to put your probabilities in list 2. And then what we're going to do is we're going to do one variable stats, but we have to tell it to look at list 1 and list 2. My calculator is probably going to die on me when I'm doing this. Okay. So we'll go to stat, edit, clear out your list. So 1, 2, 3, 4, 5. And then in list 2, clear that out and put the corresponding probabilities in the correct order. Okay, and then depending if your calculator is newer or older, the next step is going to be a little bit different. Okay, so we're going to hit stat, calc, one variable stat still, but you need to tell it to look at list 1 and list 2. If you have a newer one, it asks you what list, you say list 1, and then it asks you what frequency, you tell it list 2. Us with our older ones, we do second 1 to hit L1, and then comma, second 2 to tell it to look at list 2 as well, okay? So if you have an older one, do second 1 to get list 1 up there, comma, second 2 to get list 2 to follow it, and you hit enter. And remember, X bar is another symbol for mean, and what did it get? 2.94, okay? The reason why I'd probably force you to go more this direction is because rarely are you going to ask just mean. You'll probably be asked standard deviation as well. So guess what our next thing we're going to do is we're going to learn about standard deviation, and 1.27 would be our standard deviation because it's all right there in our calculator, okay? So this is for 6.1. I don't know if you want to label it. This is for section 6.1, this front page. The back is for 6.2. I got to keep an eye on that clock, I feel like. All right, so the next concept is seeing where in real life we can actually use mean, and they use it, and it's called expected value, okay? So the mean is also called expected value. You can use those interchangeably. So when somebody says, how many would you expect for people to be taking, it's another way of saying, what's the mean, okay? If you see the word expect, it's another way for asking for the mean. It says, because the mean of a random variable represents what we would expect to happen in a long run, The mean of a random variable is also called the expected value. It's computed the exact same way, guys. Notice it's the exact same formula. The only difference is whenever it's referred to as expected value, they call it E of x. It's the only difference, okay? It's just expected value has this new notation, E of x, but notice it's the exact same formula. We'll just throw it in our list, and we can do that pretty easily. When you see expected value is usually with word problems. So go ahead and flip it over to the top of page 3, guys. We've got some gambling here we're going to figure out. It says, in the game of roulette, a player can place a $5 bet on the number 17 and have a 1 out of 38 probability of winning. If the metal ball lands on 17, the player wins $175. Otherwise, the casino takes the player's $5. What is the expected value of the game to the player? So what we're going to do, they kind of ask us, like, what's the values, what's the corresponding probabilities? Let's just make our own chart, where the top line will be our expected random variable, and the bottom line will be our probabilities that we expect to happen. Okay, I'm just making our own little table like we had before. And these tables correspond with what are the values of the random variable. That will be x that we'll put here. What are the corresponding probabilities? That will be our p of x's, all right? So what can happen when you play roulette? Do you guys agree that you either win or lose? Okay, so I'm just going to kind of label that up here so we keep that in mind with what x would be and what p of x would be, okay? So let's focus on winning. How much do we win? What is that the payout if you win? 175. So that's our random variable x. What is your payout, or I don't know if that's the right word. What happens if you lose? They take away. So how can we show mathematically take away $5? -5. So the random variables in this case is the money values, right? You can either win and you would win $175, or you would lose and they would take away your $5. All right, so the probabilities, they gave us one of the probabilities, but we should have enough information to come up with the other one. What did they say your odds of winning was? 1 out of 38. So, with that little bit of information, what are your odds of losing? 37. You did it, right? There's 38 slots. Only one has the winning one. So that leaves the rest, the 37, to be your losing ones. All right? So guess what we can do? We can do this by hand, or we can just throw it in our calculator. It's not too bad to do in our calculator. So I'll hit Stat, Edit, I'll clear my list. And I'll clear my list. $175 is one thing that can happen, or -5. Make sure you pick the negative down here by the enter button, not the -5. Hit enter. Over here, do 1 out of 38. They'll change it to decimal, but that's okay. And do 37 out of 38. You hit enter. Is that okay? So we just make our list look like our chart. Then you hit Stat Calc 1. I have to tell it to look at list 1 and list 2. You tell it your list is list 1 with the frequency of list 2 if you have a newer one, and you hit enter. And what do you guys get? You get -26 cents. Does that look right? So the expected value of x is just the average of x, which is -26 cents. What does that mean? It means when you go play, you have, every time you play, you're going to lose 26 cents. That's not possible, right? Every time you play, you either lose $5 or you win 175. But over a long run, you can say, okay, 26 cents per game. If I pay 10, 100, 1,000 times, I have an overall idea how much I've lost, okay? So a lot of your questions are going to be like this, guys. They're going to ask you for the expected value, which is just the mean, but then they're going to extend it. It's called the theoretical. They're going to extend it to the long run. Just take your mean times your n. How many times are you playing this game, okay? So what's -26 cents times 1,000 is -$260. What does that mean? It means overall, over 1,000 games, you would lose $206. Be careful with My Math Lab because they're jerks, and we already know that, right? If they use the word lose, you might not need to put the negative. Does that make sense? They're already implying that they know it's a loss, so they want to know how much are you losing? You're losing $260, all right? If they just said, what's the expected value, they're not stating whether it's positive or negative, and that's when you want to put the negative there. If you guys mess up the negative on the quiz, don't do it all over again. Just say, hey, I put the negative 260, and it was supposed to be a positive 260 there. Okay?